Hi, everyone. Thank you for coming to my talk. My name is Abhinav Deshpande, and I'm a postdoc at the Institute for Quantum Information and Matter at the California Institute of Technology. Today, I'll be speaking about the importance of the spectral gap in estimating ground state energies. This work is jointly with Alexey, Gorshkov, and with Fefferman, who are at the University of Maryland and the University of Chicago, respectively. And this is the archive reference. Okay, so let's jump in. This is a talk about ground state energies. So I'll first define what that means. In physics, a Hamiltonian it refers to an object which is essentially a function that outputs energy given as input a particular state or configuration of a system. You can also think about it in terms of a cost function. And the ground state is just the minimum energy state of some physical system. So it's whatever configuration that minimizes the output energy of the Hamiltonian. And studying ground states is an activity that's very important in a lot of fields. It has applications, for example, in condensed matter physics, high energy physics, even quantum chemistry, and of course in optimization, because optimization problems such as constraint satisfaction problems can be expressed in terms of finding the ground state energy of some particular Hamiltonian. So naturally, this is a very important question as to studying how feasible this problem is for general Hamiltonians. And you can tackle this from the point of view of both complexity theory, which tells you when instances are hard, and from the point of view of algorithms, which tell you when some class of instances could be easy. Okay, and so one area that's born out of this is known as Hamiltonian complexity, where we typically study quantum Hamiltonians. And these you can think of today as mostly being just some exponentially large Hermitian matrix. And one of the important problems studied in this field is the so-called local Hamiltonian problem. So in this problem, we are given as input a description of some n-qubit Hamiltonian, H, which is a sum of local terms, Hi. And by local terms, I mean that each term acts in at most k qubits. And by this, I mean that it acts non-trivially on k qubits and acts as the identity on the other n minus k qubits. And as output, you want to find the ground state energy of this Hamiltonian H, or in other words, just compute the minimum eigenvalue of H. And you want to do this to, let's say, inverse polynomial additive error. So this was the first base problem in this Hamiltonian complexity literature. And Kitaev showed that this problem is QMA hard. And QMA is simply a quantum generalization of the class NP. So it means that it's very unlikely that even quantum computers can solve this problem in general. So more recent work due to Fefferman and Lin showed that it's p-space hard to solve the same problem if you want the error to be inverse exponential. And this is what we are calling the precise regime. Okay. Yeah, so let's look at what algorithms have to tell us for this problem. So we do know of efficient algorithms for some special cases, such as if you are assured that your qubits all lie on a line with 1D connectivity, and you also know that there is a spectral gap, meaning that the lowest eigenvalue and the next lowest eigenvalue are separated by some constant amount, then we do know of an efficient classical algorithm to find the ground state energy. Similarly, if we have a state with high overlap with the ground state and also the existence of a spectral gap, then there's a quantum algorithm to find the ground state. But for other cases, like we mostly have a lot of heuristics, and one very popular heuristic algorithm is the variational quantum eigensolver, also called VQE. And this has been widely successful, and it's fair to say that we don't understand why. So one question is, how do these results fit in with the hardness results that we saw earlier? So first off, the thing to observe is that the original hardness result is too general, because it just applies to arbitrary k local Hamiltonians. And presumably, the Hamiltonians that we are seeing in nature, for which heuristic algorithms are performing well, have possibly some more structure to them. Although this original hardness result was too general, like you can still add on reasonable restrictions to the Hamiltonians and still get some analogous hardness results, such as you can study q dits in 1 dimension, or q bits in 2 dimensions, and translation invariant Hamiltonians. And you can even restrict the Hamiltonian to consist of terms chosen from a particular set, which gives you all these named models in physics, such as the Heisenberg model or the Bose-Hubbard model, so on. And in all of these cases, we know so far analogous hardness results hold. So what we aim to do here is to identify a structural property that sort of bridges the two results that we know of. And identifying these structural properties would help us void generic hardness results. And they help us identify features that can be exploited by algorithms. Okay. So our results concern 2 ways of adding structure to the local Hamiltonian problem. So let's talk about what these are. Okay, the first structural property that we will study is the spectral gap. So many interesting Hamiltonians seem to have a spectral gap, and which I already mentioned earlier. It's the difference between the smallest and the next smallest eigenvalue. The spectral gap is often associated with nice properties such as existence of tensor network representations and so-called entanglement area loss, which have been rigorously proven in 1D, but conjectured for higher dimensions. It also implies easiness in various senses. So the performance of the adiabatic algorithm is decided by the minimum spectral gap from the initial Hamiltonian to the final Hamiltonian. And as I mentioned earlier, it's also easy to compute ground state energies in 1D. On the hardness side, though, we do not know much about how the spectral gap affects the complexity of the local Hamiltonian problem. So yeah, even if we have an inverse polynomial spectral gap, we do not know if these aforementioned hardness results continue to hold. And our work is an initial piece of evidence that the spectral gap makes the problem easier in general. Okay, so let's see how. So we have a provable setting where the spectral gap affects the complexity. And the problem we are considering is to compute the ground state energy of a delta gapped Hamiltonian, where I mean that the spectral gap is at least delta. And we want to compute it to inverse exponential precision. Okay, and so when delta equals 0, which means that we are only assured that the spectral gap is larger than 0, which is just a vacuous promise, then this problem is p-space complete. And this power is essentially stemming from the fact that we are looking at inverse exponential precision. Okay, so in this context, we show that the moment you add an inverse polynomial spectral gap, the complexity of the problem goes down from p-space to pp. And stated another way, the spectral gap probably makes the problem easier in the setting. And by that, I mean the setting of inverse exponential precision, or the precise setting. And of course, this assumes that p space is not equal to pp, which is, I would say, a fairly reasonable assumption. So we think that this is weak evidence that it's true in general, meaning that it's true, meaning that the spectral gap makes the problem easier, even outside of the inverse exponential precision setting. The second structural property we'll be studying is that of an existence of classical descriptions of ground states. In physics, we often want these non-trivial polynomial-sized descriptions of ground states from which we can efficiently compute certain properties, such as, say, the energy or some local observable. And it's not obvious that these descriptions exist, but for some cases they do. And some examples are, say, tensor network descriptions from which you can compute observables. Another example is, say, that of an explicit description of a polynomial-sized quantum circuit that would prepare the ground state. Now, this may not be useful classically, but if you have a quantum computer, then you can, go ahead and prepare the ground state and then study its properties. So, do such descriptions always exist for local Hamiltonians? It's not clear a priori. And yeah, if the answer turns out to be yes, then that would imply that two complexity classes are equal to one another. So QMA is just the analog of, it's just a quantum analog of NP, where Merlin gives a quantum witness and Arthur has a quantum computer, whereas QCMA is another quantum generalization of NP, where the witness is classical, but the verifier is still has a quantum computer. Okay, so the difference between these two classes, QMA and QCMA, is essentially all about whether ground states of local Hamiltonians have efficient classical witnesses for them. And given that this question of QMA versus QCMA is so interesting, no doubt there has been work done on it before. So we know that there's some oracle evidence that the two classes are different. So yeah, this is asking the question of how rich is this set of states with polynomial circuit complexity. And for example, whether it encompasses the set of ground states of local Hamiltonians. And there's not really a nice analog of this question for NP, because every bit string or every witness can just be prepared with a depth 1 circuit that is aware of what the instance is. Yeah, so quantumly, the ground state of some local Hamiltonian could need an exponentially long quantum circuit to prepare it. Okay. So our main result concerns this, our other main result concerns this structural property. And okay, so we asked this question of how important is the existence of classical description if you also have an inverse polynomial spectral gap. which is similar to the question we asked earlier. And again, we study this problem in the regime of inverse exponential precision. And the answer is that it's not so important. So in other words, if you have an inverse polynomial spectral gap and you have a classical description, the problem again is PP complete. So again, to phrase it another way, this extra promise of low circuit complexity made no difference if you already had a spectral gap. And there's a very suggestive explanation for this previous result. So here's a conjecture, which is that if you have a spectral gap of inverse polynomial in N, let's say, then it implies that you can have a polynomial sized circuit to prepare some low energy state. And this conjecture is in fact a stronger version of result 2, in the sense that it would imply the result 2. So it also implies something stronger, meaning that it would say that most natural Hamiltonians have short circuits to prepare the ground states. And this is, as I said earlier, it's not an obvious property. And this would explain why variational algorithms such as the VQE and other heuristic algorithms seem to perform so well, because the Hamiltonians of interest usually have at least a constant spectral gap or an inverse polynomial spectral gap. And this conjecture would imply that the two classes QMA and QCMA in the presence of a spectral gap coincide. And in fact, we have proved a version of this for the case where you consider inverse exponential precision. So that adds this modifier precise to the two classes. Okay, so I'll just broadly describe our proof ideas. So for the PP upper bound in both cases, what we do is prepare a thermal state at low enough temperature. And a thermal state is just one given by the Gibbs distribution. So if you have a constant spectral gap or even an inverse polynomial spectral gap, this would ensure that the thermal state has pretty good overlap with the ground state. And because of this thermal state representation, you can write out the energy in terms of a large sum, which can be computed in PP. As for the lower bound, we modify this construction of Abhinav et al., which proved that adiabatic quantum computing is universal. So we actually use another tool called the small penalty clock construction. And this is a technique that we've come up with, which allows one to use perturbation theory and helps keep track of eigenvalues and helps you lower bound the spectral gap of the resulting Hamiltonian that you get after the reduction. So in other words, it can be viewed as a spectral gap preserving reduction. Okay, so to conclude, here's a summary of what we know about the local Hamiltonian problem when considering inverse exponential additive error. In the case where the spectral gap was only known to be larger than or equal to 0, or in other words, when there was no when there was only a vacuous promise on the spectral gap, the problem is p-space complete when you have a quantum witness, and NP to the PP complete when you have classical witness. And the addition of a spectral gap of inverse polynomial immediately reduces the complexity of both cases to PP. But in the classical case, the reduction of complexity is, not more stringent, in the sense that you do not go even further below PP. Yeah. So that's what motivates our conjecture, that the spectral gap already implies the existence of polynomial sized circuit or a classical witness. And this would explain why VQE works so well in practice. So as for open questions, we can study the case of a constant spectral gap instead of an inverse polynomial spectral gap and see whether the complexity can reduce even further. The non-precise regime, or in other words, the regular case of inverse polynomial additive error as opposed to inverse exponential additive error, is obviously a really important case. And yeah, there might be nice connections to ALRs and tensor network representations in physics. So, okay, here's a poll on the conjecture, which I again have restated here, which is that a spectral gap of inverse polynomial implies a polynomial sized circuit to prepare some low energy state. I would like you to vote on this conjecture, which you can do by going to this link. So there's 4 options: true, false, undecided, and not so interesting. So yeah, if you go to this site, you will see a poll here. And yeah, I'll take a moment there. Okay, and in case you are curious, the results as of the time of me giving this talk from previous iterations of this talk have been as follows. And with that, I thank you for your attention.